All right, so I'm putting together this video because there was a question the other day in the exit tickets about vectors and vector triangles and vector, I think, parallelograms. I'm not exactly sure what was being asked, but one thing that was confusing was making shapes like triangles, four-sided shapes from lines in a diagram. Does it matter how you do it? How do you know when you need to draw it? And so I'm not exactly sure what's being referred to, but I think it might be along the lines of stuff like this, where you have the resultant of two forces. You can draw out, instead of having the P and Q here, you could draw out a parallelogram and then form the resultant. Additionally, there's things like the vector addition rule. So adding vectors by connecting them tip to tail and finding the resultant that way. So we're going to go through this, and I'm going to do a couple examples here, and hopefully things will become a little clearer. So what I have here is I drew out three vectors, and in class I made a comment. I said, well, you could take a ruler and protractor and stuff, and you could draw the vectors out to scale, and that's the same thing as solving them trigonometrically. So what I'm going to do is I'm going to use graph paper here so that I can draw the vectors to scale, and because I have a nice grid, I can keep the same slopes and such. So the first way we're going to do this is, what's the resultant? So we're going to try the parallelogram rule. So we've got three vectors here, and all I'm going to do is I'm going to draw a parallelogram using each set of vectors. So first I'm going to take two vectors, like for example B and C, and I'm going to get the resultant using the parallelogram rule, and then I'll have a new vector, which is the result of B and C together. Then I can take the resultant of A and this new vector, whatever that turns out to be, and then we can find the overall resulting vector. So let's draw this out. So I'll actually just start right here on this diagram, and let me use blue to indicate. So I'm going to take the B vector. The B vector is going down, straight down by 5 increments. So I'm going to draw it over here. And again, this is it's technically a rectangle, but all rectangles are parallelograms. Not all parallelograms are rectangles. And then I'm going to take the C vector and just redraw it right here. All right, so the resultant is actually the diagonal, all right? If I have this point here, let's call it point Q, and I pull to the right with 7, and I also pull down with 5, whatever the units are, 5 pounds, 5 newtons, 7 newtons, I'm going to wind up with a resultant like this. So let's call this E. Right? And notice I can write each of these vectors. Each of these vectors has components in the y direction, the x direction. So E has, let's see, 5 down in the y direction and 7 over in the x direction. So this is the resultant of B and C. So now I'm going to redraw this, and I'm going to draw A and E together, right? So I'm going to replace B and C with E, because E is the resultant between B and C. And E runs, let's see, we said 5 down and 7 over. So E is going to run like this. So this is A, this is E. So now I can take and make a new parallelogram. So I'm interested in, again, how A and E act on point Q together, and that's going to be due to the resultant. So I'm going to use blue pen again. I'm going to draw the resultant. Now, I have to be careful. A is going, it's got a slope of 1 to 1, so essentially a slope of 1. And I'm going to bring it over here. And so I'm going to go from this point, I'm going to go down 5, 1, 2, 3, 4, 5, and then over 5, 1, 2, 4, 5. So that's vector A. And then vector E goes, again, let's just double check our math. It's down 5 and over 7. So 5 down, 7 over. That we drew that correctly, so that's good. And the resultant here connects from Q to the other end of the parallelogram. And we'll just call this, let's call this F, because we're so creative. F. All right, so this is the resultant. So the resultant vector is, let's see, F. Now, I can write this all in IJK notation, right? So let's look at what F does. Well, if we're using, again, positive directions, X and Y, right, I and J, well, F is a vector that goes in the I direction from Q, it goes over 1, 2. So 2I, and then it goes down 5, 10. So minus 10J. So let's just double check everything. We're going to 1, 2I and 10J, right? So 2 in the positive I direction, negative 10 in the J direction. And we can get the same result if we go back to the original set of forces. Let's write each one of these forces out in IJK notation and then add them up. So vector A, maybe I should use black pen for this, it's a little clearer. Vector A originally was, negative 5I, negative 5J. So negative 5I minus 5J, right? Vector B was just negative 5J. And vector C was, plus 7 or 7I. So if we add these up, we add A, B, C up, we have, let's add up all the I terms. We got negative 5I plus 7I. Oh, that's 2I. We'll call this the resultant. And then we have negative 5J and negative 5J minus 10J, right? And we see this matches what we did graphically using the parallelogram rule. So this is just, again, two ways of doing this problem, right? One is using IJK notation. The other one is actually graphing it, sketching it out. Now, you would, if you had angles and lengths, right, you would just use the geometry information and your triangle, your ability to analyze triangles using law of sines, law of cosines, and Pythagorean theorem, and you could figure out, E and then F using angles and geometry, right? So that's just one way of doing a problem. I'm just going to pause this video and switch sheets here for a minute. All right, so what I did here is I sketched out basically the same vectors. I threw in this arbitrary D, and I say, okay, find the resultant and vector D that results in static equilibrium. Now, I'm going to do this a little differently. I'm going to find the resultant first. And I'm going to do it by adding the vectors up tip to tail. And I just want to go back to this slide real quick. This slide over here, if you look at this first example, concurrent forces, they all pass through the same point, right? You can find the resultant by adding up the vectors. So P plus Q plus S, right? And they're going to act on point A. The resultant is going to point from point A to the end of the sum of the vectors. So this is what vector addition is. You're taking vector P and adding vector Q and then adding vector S, and the resultant is the addition of all those. And we're going to do this on graph paper, and you'll see what that looks like. If I can get this, there it is, get this back. All right, so I'm going to start, let's start with vector B. So I'm going to start with vector B. Let me label this point Q again. So vector B goes down 5. All right, so this is vector B. And vector A goes down 5 and over 5. Let me use a ruler for this. Vector A. And then vector C goes over 7, right? It'll be like this. And the resultant is the addition of all these, I forgot to label this C. So A plus B plus C, where did that bring you? It brings you from the starting point, which is point Q. So these vectors all add up, acting on point Q to form a resultant that goes from Q to the end of C here. This is our resultant, right? And notice this resultant is, let's see, it's 2I minus 10J, right? So this resultant is the vectors, and those vectors add up to be 2I minus 10J. And this should look familiar because this is the same thing we got when we used the parallelogram rule, right? 2I plus or minus 10J, same exact vector, right? And we can do this adding these vectors up in any order we want. So let's try adding them in a different order. So let's try going down here. Let's do B again first. So vector B goes down 5. And then let's put C in there next. So C goes across by 7. And then A goes down 5 and 5. So 5, 1, 2, 3, 4, 5. Gotta be careful because crossing the line here. That's vector A. And the resultant again goes from Q to the sum of these vectors. And you can probably already see this resultant here. Let's write it right here. Well, it goes over 1, 2, right? 1, 2, and it goes down 10. So that's 2I minus 10J. And then we can add these up in a different order. So let's do, instead of, we have BCA, let's do C plus A plus B. So let's start over here. Let's move up a little bit. I'll start at this point. This will be point Q. And we'll say, all right, let's first use vector C. So vector C goes to the right by 7. And then, again, you can add either one. You can add A, you can add B. Let's add B to this, right? So B goes down, straight down by 5. And then A goes down 5 and negative 5. So 1, 2, 3, 4, 5. That brings us here. 1, 2, 3, 4, 5. So that brings us here. And again, the resultant vector goes from, it starts at point Q, and all these vectors add up to the resultant, which looks like this. And again, I think you can see here, the resultant is, let's see, in the I direction, we go over 1, 2, so 2I. In the J direction, we drop 5, 10, again, minus 10J. So you can add these vectors in any order, right? And you should get the same resultant. We've done this graphically 3 different ways. You can do it a 4th way. You can do CAB. That would give you the same resultant. So you could try that again on your own. And then we see, all right, this is the overall system. This is what our resultant is. And if we want to answer the other part of this question is, find the resultant and vector D that results in static equilibrium. Well, static equilibrium, so for static, if I can spell static, equilibrium, the sum of the forces equals 0, right? And this means that the sum of the forces in X equals 0, and we're in 2 dimensions, so we only have to worry about some of the forces in X and some of the forces in Y equals 0. And if these 3 vectors form a resultant that has this, right? If we want the sum of the forces to equal 0, we say, all right, well, vector D plus vector R has to equal 0, right? So that means D is equal to negative R. So the D vector is just taking the negative of all those, right? Negative 2I plus 10J. So we can, and you can see here, if you add R to D, you've got the I components, 2 plus negative 2, that's 0. Negative 10 plus positive 10, that's also 0. So again, this is kind of showing you graphically how you can do this problem. You can do it using the parallelogram rules. You can, you could break things down into triangles as well. I didn't show that method, but I think that's the one people are most familiar with. And then you can also add vectors tip to tail like this. And let me go back into the slides for a minute, and I will show you something if I can find it. All right, so this is probably as close as I can find. This is one example of having an unknown force. So you've got 3 forces here, and these 2 are unknown. Now you can see that the sum of the forces on a certain point have to equal 0. So if you knew 2 of the vectors and you didn't know the other one, you could figure out the other one. In this case, they don't know 2 of them, and they're using geometry. And I just want to show you graphically how this might play out as well. So what I did is I copied that same problem as before. Again, I've got, oh, I didn't copy this exactly. Vector A is wrong. Let me redraw this. All right, so I did this problem out again. We got the same 3 vectors, A, B, and C, and I sketched in D. I don't know what D is, but I want to find out what is vector D so that the sum of the forces equals 0. Now, we already did this using the resultant. So we found the resultant, and then we said, oh, D has to add to the resultant to make it 0. In this manner here, we add all the vectors and we find the resultant. We're going to take a different approach. We're going to say, all right, we're going to add these vectors up. And if you add A plus B plus C plus D, you should return to the starting position. So we're going to do that. Let's start with B here. I'm going to go straight down. Again, it doesn't matter which one you start with, as long as you're consistent in your drawing and you're accurate, right? So this is Q. I forgot to label Q here. All right, so that's B. B goes down like this. And vector, we can do A or C. I'll do A next. Vector A goes diagonally down from here to this corner. Vector A. And then vector C goes over by 7. So 5, 6, 7. All right, so now we're taking a different approach. We're saying, all right, B plus A plus C plus D, the sum of the forces equals 0. And if the sum of the forces are 0, that means we have to go back to the start. This is adding vectors tip to tail. And if the vectors add up to 0, this is our vector D. So now we drew vector D on there, and now we can actually figure out what D is. So again, vector A is negative 5i, negative 5j. Vector B is negative 5j. Vector C is 7i. And here we can see the vector D is, let's see, it's going from this point to this point. So it's going backwards in the negative x direction, 2. So it's negative 2i. And it's going up 5, 10. So plus 10j, right? And you can see if you sum these, right, we've got negative 5 plus negative 2. This is negative 7 plus 7. Right, so the sum of the vectors is 0i, and then we've got plus 10 plus negative 10, right? Plus 0j, right? The sum of the forces is equal to 0. And this is the same vector we got back here when we found the resultant And we said, oh, based on the resultant, we have to, the vector D has to be negative, right? And that's what it turned out to be graphically when we solved the problem graphically. So in this case, the sum of all the forces, including the unknown one, which is vector D, is 0. So you point D, you add D, and you add everything tip to tail. So you take the tip of one vector, match it to the tail of another one. You do that for all the vectors. And this vector here takes us back to the beginning. This diagram here means the sum of the forces is equal to 0. This diagram here is what are the sum of the forces BAC. The sum of the forces BAC is the resultant R, right? To get sum of the forces equal to 0, you have to cancel out R. So again, two different approaches to finding this problem. In this problem, we found the resultant R, and we said, oh, vector D, to make static equilibrium, vector D has to cancel out vector R, right? And over here, to find static equilibrium, we said, all right, we don't know what D is, but we're going to draw it in. We're going to add it into the rest of our vectors. Add vector B plus vector A plus vector C plus vector D. And we wind up with sum of the forces equal to 0. So yeah, that's how you deal with vectors in terms of lining them up and adding them up using the parallelogram rule. And hopefully this clarifies a little bit. And you can see with the graph paper makes it much easier to actually draw vectors to scale and move them around. You could put a whole bunch of different vectors in here. You could have vectors with varying slopes, right? 4x plus 2i, all these different combinations, and you can add them up and find resultants. Yeah, so that's what I got.